We looked at one type of problem, application problem, yesterday. We're going to look at a couple more starting today. We're still talking about generally linear equations. The techniques that you use here are similar, are the same types of techniques you would use for higher order equations or more or non-linear equations, but the solution of the equations would be more complicated, and perhaps coming up with the equation would be a little more complicated. But the general approach to converting from the situation into the mathematics is going to be the same. You're still going to read the problem perhaps many times until you understand what it's asking you to do. Part of understanding that is making certain you know what the question is. What is it trying to find out? Almost always, I think, and probably in this class you can say that always, the question will be somewhere in the last sentence of the problem. Sometimes problems have a couple of sentences that are background or scenario or, provide information that does not help you in solving it. And you need to be able to sort through that and find the important things. One of the important things is the question. When you see what the question is, that should indicate how many answers you need. And based on what it's asking, what kind of answers? Do they need to be integers? Or could they be fractions? Do they need to be positive? Or could they be negative? Or vice versa? Do they need units on them? Those kinds of things. That's all part of understanding where you're going, what you're trying to find out. If you don't know those things, it's going to be harder to get to where you need to be. So read the problem until you know what you're looking for. Once you have that, identify your key pieces of information. Numbers are almost always important pieces of information that you need to use. Otherwise, it's relationships among the various unknowns, or the knowns and the unknowns. Relationships with the numbers and the variables, that sort of thing. So identify those key pieces of information. Then decide what you're going to use for variables. X and Y are common, but you may want to use a letter that's like the first letter of the word. Or if you're talking about people, the first letter of the person's name. Something of that sort. Something that helps you identify what that variable represents. But write down what that variable represents. If a picture is helpful, like if you're doing a geometry problem, a picture can usually be helpful. Draw a sketch. It does not have to be precise. It can be very rough because it's just a visual aid to help you kind of get some understanding of where things relate together. Write down what the variable means. If you're using multiple variables, you're going to need to mark multiple things down. And frequently, multiple variables are the easier way to go than a single variable with multiple relationships. In many problems, as the ones we're doing today particularly, using a table to help you organize all that is a very useful concept. So we're going to look at using tables to do some specific types of problems. And I found it very helpful to be able to set the problem up using these tables. With the variables that you've assigned and with the information of the key words that you've identified, write an equation or equations. If you have multiple variables, you'll need multiple equations describing what you have to solve. You may, if you're using a geometry problem, you may need the formulas for geometry. That may be one of the things you have to use. Like we looked at a problem with perimeter yesterday. You need to know how to do a perimeter, or where to find the formula for the area, that sort of thing. You might need that formula in order to solve the problem. Write your equations, then solve the equations with whatever mathematical techniques are required. And once you have solutions to your equations, don't stop. Take those solutions and use them to answer whatever question was asked. The solutions to the equations might be the answers, they might not be. It could be that you need to do a secondary calculation after you have the solutions to get the answer to the question. Make certain that your answers agree with the question. Same units, that they're not meaningless values, like negative times or negative distances or things like that. Make sure that they make sense. If it asks for how many people, don't come up with 5.5. That doesn't mean anything. So use your sanity check on those to see if you're getting the right answer. And check back with the way the sentences describe the situation. Take the answers you come up with here and read through the problem again and make sure your answers match the sentences, because it might be that you made an error in converting into the equations. So always go back and check with the words. So let's look now at a particular type of problem referred to as a motion problem. Motion problem means something is moving. That type of problem will use the formula distance equals rate times time. Rate is a speed, time is time, distance is, distance. This rate has units of distance divided by time. So the rate would be something like miles per hour, or feet per second, or kilometers per hour, or something like that. So this is a formula that is used when you're working motion problems. And there are two different situations with motion problems. One situation is where you have one object that's moving. The other situation is where you have more than one object moving. If you have only one object and that object is moving, it's a very simple process. The process to solve a problem with one object is to take the values you're given and plug them in here and get an answer. The problem will need to give you two of those three values. Two of these values must be given in the problem, then you solve for the third. Doesn't matter which two, you can solve for the third. That's when one object is moving. It's a very simple process. It's really an evaluation of expressions. You plug numbers in here and calculate the unknown. For example, there's one object moving here. Just one car is driving. We're not talking about multiple cars, not talking about multiple destinations. 2.5 hours to drive from one city to the other. Doesn't matter which direction you're driving. So there's really one object. This is a one object problem. It involves a distance, a rate, and a time. Here's our time. Here's our distance. We don't know. It's asking, what's the rate? So you identify the pertinent pieces of information, like the question. There's the question. And then you identify the key words, like the time and the distance. And the other thing that's really not a key word, but you need to be conscious of, is that it is indeed only a one object motion problem, that there are not multiple objects involved. And that's not stated anywhere there that there's one thing moving. So you have to kind of interpret from how the problem is stated that there's only one thing moving. But it should be fairly obvious or completely obvious. So identify your information, then remember your formula. This is your formula. Distance equals rate times time. You need to remember that formula. It's not a complicated one, but you need to remember it. When you have a motion problem, distance equals rate times time. To solve a problem like this, there are three variables there, distance, rate, and time. Our problem is telling us what two of those values are. It's telling us a time value, it's telling us a distance value. So we know this, and we know that. There's only one thing we don't know, that. So we can calculate what that is. Plug the numbers in, do the arithmetic, and you get a value. And because our units here were hours and miles, our rate is miles per hour. So this is a very easy, simple problem. Plug the numbers in and do a simple calculation, and you have the answer. Make certain that your answer has the units. And if you know, because we're looking at a speed, you don't want to come up with a negative number. Could be a fractional number, that doesn't affect anything. But you need to put the units onto the answer, because what was the speed? Speed needs to say miles per hour, because 60 could be feet per second. That's the easy one, when you have motion problems with one object. All right, what if you have more than one object? Let's say we have two objects moving. We're still going to use that same formula, distance equals rate times time. But now the problem is much more involved. There is much more to have to be concerned with. Because of that, if you use a table to help you set up the problem, the table helps you organize it, helps you identify the things that you know and that you need to know, and also leads you to what the equation is. We're still going to use D equals RT, but we need another equation to actually solve the problem. We're going to use distance equals rate times time to set up the table. So it's still part of the problem, but it does not give us an equation to solve to get the answer to the problem. But what we're going to do is we're going to set up a table that has 4 columns. The first column is just a name. Use any words you want to there. It has nothing whatsoever to do with solving the problem. That's just to help clarify what each of those 2 rows represents. Probably it's best to use something meaningful there to help you identify. Like if you have 2 cars, car 1 and car 2, 2 people, person 1, person 2, something of that sort. Some kind of identifier so that you know that everything you enter on this row is going to pertain to that thing. And everything you enter on this row will pertain to that one. But you can call it anything you want. That's the first column. The other 3 columns are rate, time, and distance. What was our motion formula? What are our columns? Distance, rate, time. That's where the 3 columns come from, is because we're going to use this formula to help construct this table. All right, so identifiers there. The remaining 3 columns you fill in by taking information provided in the problem statement and the variables you define. Those will fill up 2 of your columns. The third column you get by solving the equation D equals RT. You're going to solve it because if you're given information to fill up these 2 columns, you can get this one by calculating this. This will be rate times time, gives that. Rate times time gives distance. What if you fill up these 2 columns? Then you'll get the rate by dividing distance by time. What if you do this one and this one? Then you'll get the time by dividing distance by rate. As long as you have 2 of the columns filled up, you can calculate the third one from the equation. And it doesn't matter which 2 you have information for. The third one can be found. So let's look at an example. Okay, before I go on. That gives you the organization of your information. The way you get the equation to solve, to get the answer to the problem, is you will use one of these columns that involves variables, and you'll either use the sum of 2 things equals a total, the difference of 2 things equals a difference, or you'll set one equal to the other. So I could have, usually you won't use the sum of the rates, but the difference in the speeds equals a certain number. One went faster than the other. That could be what you use. So R1 minus R2 equals this difference. That gives you an equation. It could be that the total time was, well, T1 plus T2 equals that total, or the difference in time, or that the 2 times were equal, or maybe it's the distances were equal, or the total distance, or the difference in distance. But there are only 3 types of equations: the sum, the difference, or set them equal. And it will be on one of those columns. The reason I can't say specifically it's on this column is it depends on what type of information is provided in the problem. It might be this one, or this one, or this one. It'll always be one of the columns, and it will always be either the sum will give a total, the difference will give a difference, or you'll set one equal to the other. And that you have to look at what it's asking for, what other information is in the problem, to determine which of the 3 types it is. So here's a problem. Krista drove to her grandmother's. Read through that. So you can read. I'm not going to read it to you. Then let's use the method that I've described for how you approach an application problem. First thing you want to do when you're when you're working an application problem is read it and understand it. And part of understanding it is to identify what? What's one thing you need to identify? What is it asking? What's this one asking? What's the distance? That's the question. So now we know we're looking for, well, we're talking about miles, so we're looking for some number of miles, right? We know something. And how many answers is that? Is it going to be a different distance depending on which way she drives? Same distance, no matter whether she's going or coming, isn't it? So it's just one answer we need. Okay, what else do we pluck out of this information? Rates. What are my rates? What other information is available there? An hour or less. Okay? And really, that's about all there is. That first sentence really doesn't provide any help at all, does it? It's scenario, setup. And returning home on Sunday, traffic was lighter. Okay, who cares why? It's just she had a different speed, right? So again, that's not helpful. So that's why you go through and highlight the pieces that are helpful. So all that other stuff just fills up space, but it doesn't help you work the problem. All right, so those are the pieces of information we have to work with. It doesn't seem like very much. But remember, we also have the fact that, is something moving here? Yeah, there's this car driving. So that's a motion problem. What do we know about motion problems? We have that formula to work with too, don't we? So we have that also. And we also have this idea of using a table to organize things and help us find what equation to solve. So how would our table look for this problem? Well, we've got, what are we looking for? We're looking for the distance. Let's make our variable be the distance. And actually, even though there's one thing moving here, it's moving two different times. So that's the same thing as two objects moving, because there are two different rates involved. So that's like two objects. So we use the same thing as if it were two objects. So we're only looking for one thing, though. We're looking for distance. So let's define our variable to be that distance. How far is it to our grandmother's house? That's our variable. Let's make a table. Our table is going to have 4 columns. The first column is just an identifier. Well, the two things that are different is she going to her grandmother's or is she returning from it? I chose to identify mine as going or returning, or going or coming, I forget what words I use, but one to indicate one and one the other, direction. So that's what I identified, going and returning. Those are my names. You could call it anything you want to. These just help you identify that everything that I put on this row is going to pertain to when she's driving to her grandmother's. Everything on this row is everything that pertains to when she's returning. Well, what do we know about these other columns? Do we have any information that we can put into any of those other columns? What numbers were provided in our problem? And what were those? Those were rates, right? Those are speeds. So we have numbers we can put into that rate column. And which one goes where? 40 up here. So we can fill that in. Given to us in the problem, no question. All right. What else do we know? 1 hour. So does that mean it took her an hour each way? How do you know it didn't take her an hour each way? Different speeds. So if you're going the same distance, it can't be the same length of time to get there if you're driving different speeds. But what else do we know? Is there anything else we can put in there? We can't put the time in because it doesn't fit. What else do we know? Don't we have a distance column? And what did we say about those distances? That's true. There's one other thing we know. It's the same distance both ways. So how far is it when she's going? How far is it when she's returning? Same thing. X can go there. Given the information and the variable, we can fill out 2 of those remaining 3 columns. How do I get this third column? Distance equals rate times time. Or rearranging it, time equals distance divided by rate. Take this formula and rearrange it. So this is one of those solve for variable situations. We solve for t in this equation. So here's our equation, d equals rt. Rearrange it to get time equals. Why do I want to do that? Because I know distances and I know rates. I have them right here. So if I plug those into here, I can get numbers to go there and there, or at least I can get expressions to go there. So take this one. What would I put in here? Well, time is going to be this distance divided by this rate. So it's going to be x over 40. And down here, it's going to be x over 48. And now I have all of my columns full. Okay, so that helps me organize it, but where does my equation come from? What is the only piece of information we haven't used from the problem yet? The hour. And hour pertains to which column? Time. And remember I said that our equation is going to come about by either adding these two and getting a total, subtracting them and getting a difference, or setting them equal? Well, the piece of information we have pertains to this column. And it says a 1 hour what? 1 hour difference, doesn't it? How do you get a difference? Subtract. And we're getting a positive number, so we need to make sure we subtract in the right order. Which one of these numbers is bigger? If you divide by a larger number, you get a smaller one. So this fraction is smaller than this fraction. So we need to subtract this minus that is equal to 1. Oops, where am I? Okay. That minus that is equal to 1 hour. This time minus this time is equal to that difference of 1 hour. Subtract the numbers because we have a difference. It said difference in the problem statement, I believe. Or well, I guess it said less than, which implies a difference. There's our equation. All we got to do is plug these in. Now we have an equation we can solve, right? And if we solve that equation, we get a value. And x, we said, if you look back, x was defined to be the distance. So x is the number we're looking for, and distance has units of miles, so it was 240 miles. I multiplied everything by 48. I got rid of my fractions. I'm combining some steps here to save space on my slides. Okay, I guess it's not 48. I multiplied by, what did I have to multiply by? Oh, I know, I'm sorry. What I did is I found the common denominator, which is 240. I need to look at what I actually did there. I found my common denominator. That's all I did. And the LCD is 240. So not a very small one, but that's the LCD. So is 240 correct? Well, let's check. If she drove at 40 miles an hour for 240 miles, how long would it take her? This is actually one of those just plug into the D equals RT formulas, right? I'm sorry? How long would it take her to drive this at 40 miles an hour? 6 hours. What if she drove 48 miles an hour? How long would it take? Is that an hour's difference? So that actually meets all the requirements of the problem, doesn't it? And notice I didn't check it in my equation. What I did is I compared it back to what the problem statement was. How long did it take her to go? How long did it take her to get back? Was that a difference of an hour? The table doesn't solve the problem. The table helps you organize the information to lead you to the equation. Because if you work with a table, then your equation is always going to be the sum, the difference, or set them equal on one of the columns. And the column you'll pick by what information has not yet been used. In this case, we had not used the hour difference, so we used the time column. Yes. Okay, I have two fractions here, right? I need to find an LCD. If I'm going to subtract these, I need a common denominator. So if I want a common denominator, I have to take 40 and I have to prime factor it. And that's the prime factoring of 40. I have to prime factor 48. And that's that. 3 times 16. My LCD then will be my longest string of 2's in either of these, my longest string of 3's, and my longest string of 5's. So this is my longest string of 2's, this is my longest string of 3's, that's my longest string of 5's. So my LCD is 2 times 2 times 2 times 2 times 3 times 5. 16 times 3 is 48, 48 times 5 is 240. So that gives me an LCD of 240. Now I need to rewrite each of these fractions. With a denominator of 240. And for my numerator, to make this become 240, what do I have to multiply this by? So if I multiply that by 6, I have to multiply that by 6. To make this become 240, what do I have to multiply that by? So I have to multiply that by 5, and I get that. And that's where that comes from. Then you just solve that equation. From here, you'd multiply both sides by 240 to get rid of your fractions. 6x minus 5x is 1x. 1x equals 240. With a motion problem, if it's a two-body type of problem, in this case there's only one thing, but it's two different trips, so that's like a two-body, then a table of this type is what you can use. Fill in the information that you know, fill in where the variable goes, use D equals RT to calculate the third column. Then with the remaining piece of information, pick which column it applies to and use that to get the equation of either adding them, subtracting them, or setting them equal. That's your equation. Solve it. Answer the question. You can work this problem without a table. That's the way I learned when I was in school. They didn't teach using the table when I took it, and it can work. Generally, it's a little more difficult to figure out that this is the equation you want. This is what you have to solve to get there, this type of thing. And that, if you don't use some kind of organized approach, can be a little difficult to get. So I strongly recommend that you investigate using the table approach for these types of problems, because they are very helpful. Okay, are there any questions about how to do the motion problem? Any comments about how to do it? Okay, here's another one. And this is actually two bodies on this one, two different planes. Can somebody paraphrase what this problem wants to know? Don't just read the problem, just summarize in your own words. What are we trying to do? trying to find how fast the two planes are going, right? And so that's our question. What information do we have to work with? And we also have south and north. And why is that important? That's important because that means they're going opposite directions, right? They're getting farther and farther apart as time goes on. They're starting at the same place and they're going opposite ways to get farther apart. And that's an important thing when you come to deciding which equation you want to use. We're still going to do that sum difference r set equal. And so that direction that the things are traveling is an important part of selecting them. So you do need to, with a two-body problem, look for, are they moving in the same direction or opposite directions? 50 miles slower, 275 miles. I forgot the 1/2 hour. I needed to underline that. Okay, so we're looking for their speeds. So how many speeds is that? I could use two unknowns. I'm going to use one. And I can have it be either one of the speeds I want. I'm going to do it be the slower one because I like to add, and I don't, rather than subtract. The San Diego plane is slower, right? San Diego plane slower. So that's the smaller number. So I'm going to let my variable be that speed. So how fast is the other one, the San Francisco plane, going? Well, but okay, how would you represent it? What's the expression to represent that speed? If this one's x, isn't that the other one? Don't make it hard. It's really a simple concept. I mean, if one's 50 more than the other one, it's x plus 50. So that's the faster one, the one going to San Francisco. So I have something that I can put into an equation for each of those speeds, don't I? So I'm going to organize this with a table. So I've already used this piece of information, but I haven't used that one. I haven't used that one. Haven't really used this different directions yet. All I've used is this piece right here to do that. So what kind of table do I need? Well, 4 columns. Name here. I'm going to identify by which direction the plane's going, or which city the plane's going to. One of them's going to San Diego, one of them's going to San Francisco. Those are my 2 planes. And what do I know about these? I don't know distances. Then what do I know? Okay, what's the rates? What rate goes where? What's x mean? No, but I mean, what does it represent in this problem? San Diego. And so x plus 50 represents San Francisco. So I know those, right? Or at least I know something to represent them. What else do I know? Where do I put the half hour? They left at the same time, and a half hour later, they both would have been flying the same amount of time, so both of them get a half for the time. I write it as a fraction usually. Decimal works. What goes here? What does the 275 miles say? What is 275 miles? Distance of what? So does that mean each of them flew 275 miles? How far apart would they be if they each flew 275 miles? They start here, and this one flies 275, and this one flies 275. How far apart are those? 550. So I can't put 275 on each of those. So what do I put there? Remember the formula? D equals RT. Don't we have R and T? Calculate D. The third column is always filled in from that formula. Not from data, you fill it in from the formula. Yes? Well, what I was trying to indicate is we're not going to use 275 as how far each one flew. It's actually going to be, they're going to be 275 apart. That's what's really true. That other thing was fictitious, wasn't part of it anyway. But that's what the table's based on, right? We know these two things. We use that to get this. So what would I put there? Here? How about just rate times time? 1/2 times x. And here, 1/2 times x plus 50. Rate times time. Just multiply those together and get that. So now I have my table filled out, but I don't have an equation to solve yet, do I? What I do have is I still have that piece of information about the miles, don't I? And I know my situation. I started here and I'm flying different directions, and at some point I'm 275 miles apart. So if this is how far this plane flew and this is how far this plane flew, what does that 275 represent? Starting here, going this way. Wouldn't you add those two distances to get that total? You take this one and you take this one, and this one plus this one gives you the total. When they're going opposite directions, you're going to add distances. If they were going the same direction, I'm sorry, that's opposite direction. If they're going the same direction, you subtract distances. Opposite directions, you add. Same, you subtract. Opposite, you add. These are going opposite directions. So you add these two distances, and that has to equal that 275 miles. That's where the 275 comes in. So here's your 275. You take this plus this equals 275. Then solve the equation. Here's your equation. And I hurriedly put this slide together this morning, so it's not exactly the way I want it, but solve the equation. So I'm going to get rid of my fractions by multiplying by 2. Solve that, and you get x equals 250. What does 250 represent? What's x? What does it mean? What? X was defined to be, the San Diego plane's rate, and x is a speed, so it's miles per hour. And so the San Diego plane is flying at 250. San Francisco is 50 more than that, so it's 300 miles an hour. Even though it's a fairly complex idea of the planes going different directions at different speeds, that sort of thing. If you organize it, then you can work out the details, and it's not that involved. So again, I strongly recommend the use of the table. And remember, when you're constructing the table, the numbers provided in the problem and the variable you define will fill out 2 of the columns. The third column must be found by using the formula distance equals rate times time in some manipulation of it. The first table, we rearranged it to get time equals distance divided by rate. In this one, we use it as distance equals rate times time, or rate times time equals distance. We knew these two. We got that one by multiplying that times that, straight across the row. In the first one, we knew, what did we know? We knew this and that, and got this, or didn't we? No, we knew this, and I don't remember what we had, but we had one of them. So you finish filling out the table by using the formula. Don't force a piece of data in there. Use the formula. If you had put 275 in for both of those, for one thing, it would have been incorrect. For another, you don't have any way to get an equation. So don't just, blindly push forward saying, well, that's a distance, it goes in the distance column. It may not go in there. A time may not go in the time column. That 1 hour that we had on the previous problem did not appear in the table. It was one of the pieces of information you used in the equation that was not in the table. Same thing with this distance. It's not in the table. It's part of the equation. So fill out the table with what you know, get the remaining part by the formula. Then either pick a column with the remaining piece that applies to the remaining piece of unused information. Either add them, subtract them, or set them equal to one another. And maybe you don't have a piece of information, but you'd have a statement like the rates were the same, or the times were the same. That sort of statement, which means you're really given 0 as your number. Motion problems. It might be that you would get a problem with one thing moving, but more than likely it would be a two-body problem where you'd need to come up with an equation. And again, it's not required that you use a table, but you might want to consider it. You will need to be able to work problems of this type. Motion problems with two things moving. Yes? No. We got speeds. We were looking for speeds. The question asked us to find the speeds. So that's what we found. We found X miles per hour. We found those two things. This is not a distance. This is a speed. We used the distance here. That's the place the distance came in, right there. Is that this distance that this one flew plus this distance, that is 275. It starts at 0 apart and grows to 275 in a half hour. And in order for that to be true, those are the speeds they had to be flying. If they'd done it in an hour, the speeds would be different. You could still do a calculation of that sort, but it wouldn't be the same speeds.